Welcome everyone to the very first session of Tesseract Talks. My name is Jason, and I'm here with Anirudh as part of FTC Team 21689 Team Tesseract. We're a community team based out of Nashua, New Hampshire, and during this past season, Into the Deep, we ranked among the top 100 teams worldwide in OPR and delivered a strong performance at the World Championships. As we head into the new season, we're expanding our outreach with a brand new initiative, Tesseract Talks. This is a live webinar series where we sit down with some of the top performing FTC teams to go deep into one specific mechanism, system, or strategy that sets them apart. Every session is recorded and shared afterwards so teams everywhere can learn and be inspired.
For our very first session, we're thrilled to welcome Team 14259 Turbo V8. Turbo had an incredible season, finishing with the 25th highest OPR in the world and competing strongly at the World Championship. One of the biggest contributors to their success, especially their best in the world DC sample average, was their active intake system. So today, we're diving into everything: active intake versus claw design decisions, geometry, iterations, transfer, sensors, and more.
Let's start the discussion at the beginning. When and why did you decide to use an active intake over a claw? How did you evaluate them against each other? And did you guys test both before making a decision?
Yeah, sure. So we wanted to use an active intake if we were able to figure out how to do it pretty well. We knew this basically by day one, and we knew this because historically active intakes do significantly better when you're intaking an element in a random area. For example, in seasons like Rover Ruckus, Freight Frenzy, and Ultimate Goal, you notice that all of the top robots are using active intakes, and claws just require way too much precision for those use cases. We've tested both. Our V1 robot was a pivoting slides robot. It had a claw on it, and we had not found a solution for active intake yet, which is the main reason for us using a claw. And we found that the claw was able to be defensed on. So at these league meets, we noticed that we were being pushed around, and we were able to push around other robots that had claws, and intaking from the submersible was fairly difficult. With a claw. So we decided that we would never be defensed on again, and then we continued developing our active intake.
So yeah, that decision process sounds great. And so once you decided on your active intake, what different iterations have your active intake prototypes gone through, and what different intake archetypes did you test?
Sure. So I'm gonna go in order from left to right and then down one, left to right again. So for the first image, we can see that I guess the right intake top left, we can see the intake is being intook like horizontally, and it has to go up a ramp. But if you notice, there's also some wedges and notches in the bottom ramp to allow space for the surgical tubing to spin. But we had issues with the sample being rotated, and the wedges inside of the sample would actually get stuck inside of these notches. So there were too many jam cases for this intake. For the second intake, um, we were able to intake blocks horizontally as well. The surgical tubes were like slightly offset from each other to hopefully help with orientation, but they did nothing for orientation, and blocks would get stuck on the sides. So if a block was turned, it would tend to get stuck on the side walls, and we could also fit multiple samples vertically inside of this intake. And I believe there was also a case where we could fit two samples horizontally, one on top and then one on the top in the back, and then one on the bottom in the back. So we were basically able to fit two samples in many orientations, which was not optimal. The third intake was uh, it performed like fairly well. So it was able to intake the sample horizontally, and um, it wasn't able to fit two inside of it. The sidewalls did not jam on. They did not get jammed on. So you can see like there's a diagonal cutout instead of a more like rectangular shape. So um, there were no like extreme jam cases here, but the main problem with this intake was that it was also able to fit two blocks. It was able to fit two blocks in like the hot dog orientation if they were side by side and tried to enter. So that pushed us to our fourth iteration where we wanted to handle intaking the hot dog style blocks. So the intake we came up with, it has a little arc on the bottom. You can see through like the clear intake that there's this arc that kind of is like pretty thick. So it was like around like 1 centimeter or like something along those lines. It was a 1 centimeter thick lip that's arced, and the main purpose of this was that the surgical tube rollers were meant to get inside of the wedge inside of the block, so that little triangle shape. The surgical tubes were supposed to hit the indent there, and then the block would rotate. And the rotation of the block was supposed to pull it into the intake rather than like the block going up a ramp. So instead it was supposed to roll into the intake. Um, but the main problem with this was that the motor slash like the surgical tubes were grippy and strong enough to just hold on to like any vertical blocks, so it didn't perform as intended. And then this intake also required like a decent bit of surface area to deploy down. For the fifth intake iteration, we have these side sweeping surgical tubes in the front, and then we have gecko wheels in the back. So the main purpose of this was that the side sweeping wheels would help turn the block into like the hot dog orientation, and they would funnel them in a bit, and then the gecko wheels would get grip of the block and then push them into the chamber. So the main problems we had with this was that it was very bulky, and it was hard to deploy into the submersible. Blocks would also run away from the surgical tube rollers if they weren't aligned into the intake. So unless the block goes into the intake, if it misses, then it would like shoot it out into like the corners of the submersible. And we knew that this would be unacceptable at a high level because blocks would be scarce, and you really want to have like good access to like a lot of blocks inside of the submersible at the highest level. So we moved on to this sixth iteration, which is very similar to the fifth iteration, but it has a hollow bottom, and it also has gecko wheels in the front instead of surgical tubes. So blocks would run away less from this intake, and there were no jam cases. Basically, it was able to orient blocks perfectly. It was able to like intake also near perfectly. To deploy the intake down, we planned on using a virtual 4 bar, but we still had one edge case where if we deployed the intake onto a block, it would be like pretty tough to get the block. It would be pretty tough to like get the block and deploy the actual intake into the submersible. So that moved us to our seventh iteration. It was just supposed to be a final version of the sixth iteration. It was like more finely tuned, and we had a latch inside of the back to eject blocks out. And we were actually planning on using this intake. We had a full robot catted, and we were just about to pull the trigger, intake, and go for that intake on a new robot. And then at the last minute, we decided not to because when doing some more research, we found people testing intakes that were like our eighth intake, and um, it looked pretty promising from like videos we had seen, but we weren't sure if like people were like hand picking out these videos. So we tested it ourselves, and this intake intakes hot dog style, and it just has two surgical tubing rollers on top. It was much simpler than anything we had developed in the past, and we were hoping for some promising results, and we definitely got them. So this showed us that this intake kind of showed us that if the block was perpendicular, if it was horizontal, yes, it would jam. But it also showed us that if there was any offsetting in the system, if the block was more slid to one side, if the block was like mostly straight, that it would intake it pretty well. So we saw the potential in using top rollers instead of side rollers, and we saw the potential in intaking hot dog style with this intake, which moved us to our um I guess ninth intake. And this ninth intake is kind of where we really saw the potential of the counter roller arcs, and I kind of like had to develop our orienting geometry. So um in this ninth intake, you can see we have top rollers and a counter roller, and then we also have our arcs. So the arcs allow the intake to pull the block in further before being forced to like jam up if it didn't orient the block, or if we would like kind of hold on to like a second block through that perpendicular jamming. So um I guess this intake really showed us that we could intake at various angles because of that counter roller, and then it also showed us that um, the wedges worked really well for kind of turning into blocks, and then it showed us that the top rollers slash like the top piece needed to be very precise if we wanted to intake well. So some flaws with this intake were that it was not too. It was pretty long, so we were able to fit one block inside of the chamber, like you can see in this picture, and we were able to fit a second block that was perpendicular to this, and it would generally get stuck inside of the wedges. So in the 10th image, the final image, we solved all of these issues. We made the intake shorter. Um, we moved the top rollers up and we changed the top piece geometry to have more lenience for blocks to enter. So the range that blocks could actually enter the intake in, even vertically, was amplified a ton. We also kind of changed the counter roller material. We found that like that mattered a decent bit, but the counter roller doesn't truly help with the intaking process. It just helps with dealing with different angles. We also added a latch to the back of the intake. Now that latch allows us to reject blocks out of the back, and then it also allowed us to transfer the block through the back.
Yeah, those iterations are all super awesome. We got a couple questions about your iterations submitted in advance. So, what materials have you used throughout the iteration process? Have you found that 3D printed intakes break frequently? And what materials are you using on your intakes now? Also, how long did this whole iteration process take for you guys?
Yeah, sure. So, for the materials we have used on our iterations, we mainly print out of PLA. So, I guess everything structure is printed out of PLA, and some of these rollers in the images we tried printing out of TPU with the hopes that they would be like we could change the stiffness of the rollers and figure out what was best. So, like with surgical tubing, you're stuck to like kind of one stiffness, but with TPU, you can just change the infill and like the amount of walls you have to test different strengths out. So all of the parts are made of TPU and PLA. One thing is for one piece on our final intake, the top piece, our micro servo latch in the back is mounted to that PLA piece, and we had issues with that PLA piece breaking because the block would enter with a lot of force, and since the intake was short, those surgical tubing rollers would constantly put like a lot of force on that PLA servo mount, and then that servo mount kept snapping. So we switched the whole piece for TPU and made the parts slightly thicker, so the whole like servo mount can flex a bit, which just prevented it from breaking altogether. So we haven't had any 3D printed intakes break at all, other than that top piece on our intake. And we're on our current intake, we're using a combination of like TPU and PLA on the intake. So for how long we spent brainstorming and iterating, in terms of brainstorming, we probably spent around like a couple days really just trying to figure out what intake to like start off with because we knew that like brainstorming only takes you so far, but you truly have to like continue testing in person and with like your physical prototypes to actually figure out what's going to work. And in terms of like how long we spent iterating, we spent quite a lot of time. So we started in like week 2, and then we had something similar to our final design by like December, but we made small tweaks like throughout the season. So like we would raise the intake up a few millimeters to account for slide sag. We would like change the geometry of the top piece, change the geometry of the bottom piece, like figure out how we can make transfer more consistent. So even though like we had the concept down, we continued making small tweaks throughout the season until like June, even like days before MTI. There were still like very small iterations we were making to help with our transfer, to help with like intaking, to solve some small jam cases, and etc.
Walk us through your intake geometry. Why did you decide to drop down while intaking? What small changes helped your intake speed? And why is the back of your intake empty?
Sure. So the intake, I guess, geometry mainly works by having some semicircle arcs on the side. So there's one semicircle arc on each side. There's also a wedge on the left side of the intake, um, that kind of sticks out near the semicircle. So earlier I talked about how a block could get stuck perpendicularly in that semicircle, but that wedge prevents it from being perfectly perpendicular. And the rollers are also offset from each other. So that offset in the rollers and that offset through the wedge allows us to orient the block and rotate the block. So the surgical tubing is pretty stiff, so it's able to do this like very quickly. And because of that, they also break a lot because if you can imagine like the rollers putting in a lot of force at its like point where it's mounted, it tends to like bend a lot, so they break pretty often, but we just replace them. Like it's not like multiple times a match. It's like once every like few matches. So we run through a lot of feet of surgical tubing very quickly. Now, um, the entry geometry allows for a lot of lenience vertically. So there's a lot of vertical space. Like there's much more vertical space than you'd probably imagine for an intake like this. So the block can like basically enter however it wants, and then the vertical and horizontal, I guess the vertical space converges. So the bottom piece is angled up and the top piece is angled down. So when it enters, there's a lot of space, but as it travels through, like the space kind of closes up and they eventually converge to basically be the height of a block plus like a couple millimeters. Because um, as soon as you like go too tight, like your block is gonna have a hard time fitting through the gap. And in terms of like side to side tolerance, there is a ton of space. The intake is around like 55 millimeters. The two plates are around 55 millimeters away from each other from like the inside. So there's like plenty of space for the block to wiggle around, but it didn't matter for us. Our transfer was designed to work like this.
We got another few questions submitted in advance. Are counter rollers important for intaking speed? And does the size of surgical tubing impact the intake speed?
Yeah, sure. So we found that the counter roller was not that important for the intaking speed, but it was good at handling some edge cases. For example, if we were to deploy onto a block, the counter roller would kind of put force on the block, and then the block would be pulled out in front of the intake, and then the top rollers would pick up the block. So we found that like the counter roller helps with that edge case. Also, because we intake top down, um, we were able to utilize the counter roller to be able to drop onto a block, like I just said. So that really helped with I guess being a top down slash also horizontal intake. So what I mean by top down is you can see in that first picture for the empty back for sample ejection, the intake slash like the block is basically facing up. So the intake can pivot to be vertical like that, but also the image at the bottom, it can pivot to be horizontal where we have like the drop down intake style. So um, both of those allow us to deploy onto blocks and deploy into the submersible in a way that we don't disrupt the submersible a lot. And there's no way we can't deploy our intake into the submersible. So that's the main reason for like pivoting top down. And then the counter roller is so we can deal with those multiple angles. So like when the intake is able to intake at so many different angles, you can't have a ramp that works perfectly for any specific angle. So you need that counter roller to act as a ramp at any angle because it's a circle. And um, also, the counter roller allows us to account for slide sag. So as we extend, our slides tilt downwards a bit. The Misumis have a little bit of play in them, so the intake will be lower than it should. And this caused it to basically jam up completely. Like we were able to intake with no extension perfectly, and when we went to full extension, we literally cannot fit a block in. So we have to pivot the intake upwards as we extend. We have inverse kinematics for this, and that allows us to intake at multiple angles. But you can imagine that the intake becomes pretty steep when we start to get towards the end of our extension, which is where the counter roller really helps because it doesn't feel like it's steep to the block. It just goes up the powered counter roller.
Yeah,
Um,
that oh,
yeah,
yeah, so that geometry is super cool. And a major part of every intake design is to account for transfer. So what design adjustments have you made to your intake to improve the transfer's consistency? Did you initially design your intake around transferability, or did you optimize for transfer later?
yeah, sure. So, originally in our intake, like we didn't really consider the transfer too much, but we knew that the transfer was not the hardest part of the robot. We knew that definitely like working on the actual intaking process was because once you have the intake done, you can basically choose like any way to transfer. You can transfer out like the front. It just depends on like the pivot geometry you end up going with. And this just ended up working best for us because um we wanted to be able to transfer blocks out the back. So, I mean, we wanted to be able to, first of all, reject samples out of the back. And since we already had like a latch gate there, we knew that like just being able to transfer from that same area was just like it made the most sense because we didn't have to add any other like actuation. So we just put a cutout in the side of the intake and that allowed us to actually like intake to block, but to make it more consistent, um, we had issues where our horizontal slides would not be like precise enough because we started off using linkage slides, so it was powered by a motor on like a 2 bar linkage, something similar to that. And it would bounce a lot. We got no precision and we were unable to transfer for our first league meet. We quite literally did not transfer a single block. And at our league tournament, we switched to string and were able to transfer, but it still wasn't perfect. The claw was trying, it was getting stuck on the intake a lot, and we switched to a thinner claw. So inside of that cutout, the thinner claw would be able to kind of grab much more with like a little bit more margin of error. But we still had issues with our horizontal slides coming in with a lot of force, and they would bounce out a bit, and that thin claw did not have enough margin of error. So over time, we continued iterating, tried a bunch of different claws out. But eventually for MTI, we came up with this setup. So right here, you can see there's some wedges on the intake, and the claw is a triangle. So it's pretty thick, actually, the claw, but it's a triangle, and that triangle meshes with the triangle and the wedge. So both of them kind of mesh with each other, and then they slide inward. So as the claw closes, the triangle on the claw and the wedge will align, and then it will kind of guide the claw to go inside of the intake, and that doubles our margin of error. And we also put a hard stop on the arm, so we had issues with some backlash on the arm, not allowing us to be like very precise. So we put a hard stop that we can kind of stall against to make sure it's always in like the right position every time, and that we have no issues with kind of less precision needed.
Yeah, that makes a ton of sense. So now let's go through your sensor usage. What sensors do you use in autonomous and teleop? Do you have sensor-based transfer adjustments? And a question we received beforehand, do you use computer vision in auto?
Yeah, sure. So for intake and transferring, we have a color sensor inside of the intake. So if we have a block, we will automatically transfer it. If so, as soon as we pick up a block from the submersible, we just we like flip up the intake, retract the intake, and then use the claw to pick it out, and then just get ready to deposit. But if it's the wrong color, we'll automatically reject the sample. So many teams spit it out through the front, but something special we do is we open the latch in the back and then spin the vertical rollers so the block will actually fly out the back, which makes it harder for the other alliance to grab, and it requires no slowdown of intaking for the next block for us. So that's our back rejection. The robot will also drive to the basket and deli up, so the driver does not worry about like what's inside of the intake, or they don't need to like react fast to what's going on inside of the submersible. They just need to get near a block. So the way that works is I said earlier, like the transfer automatically happens. So while that's happening, we also trigger a drivetrain command to drive to the basket, and it's overridden by the joysticks. So basically, if the driver uses their joysticks while this is happening, it will automatically override that auto drive sequence, and then the driver gets control back. So like the first like 300 to 400 milliseconds of our intaking process and probably movement process is automated, and that cuts out some like human reaction time. So um, we also have some sensors. I guess inside of the intake, like there's the color sensor, but that also tells us if our transfer has failed. So if we try to like use the claw to pick the block out of the intake, um, the block will obviously come out of the intake, and then the color sensor can no longer see a block. But let's say we do that sequence and the color sensor still detects a block. We know that that block was not pulled out of the chamber, and we can try again. So that's like some fail safes we use. We're also planning on using the fourth wire on our claw. So these axon servos, you can read like the position they're at. So just by like reading the actual angle of the claw, we can tell if like the transfer has failed or not, because the claw will close slightly more if we don't have a block, and it will close slightly less if there is a block inside of the claw, because I guess there's the thickness of the sample. So that on its own can tell us like if we've intook a sample or not, so we can have like a much faster transfer fail safe than just using that color sensor. So the intake's motor encoder also tells us the velocity of our top rollers. So based on the velocity of the top rollers, we can tell if like the intake is jammed or if the intake got like stuck on something, and we can just know more about our intake. So there's more jam cases on our intake than like people think, but it's basically handled instantly by software. So there's a I guess like a jam case where the block gets rotated like 45 degrees inside of the intake, and we map out the velocity range for this type of jam. And if we notice that the intake is spinning at roughly that velocity range, we will start an unjam sequence. Same thing with if the intake is not spinning at all. We know that like it's completely jammed if the rollers have like if the velocity is like close to zero. So we'll also start an unjam sequence fairly instantly. So I guess those are kind of the sensors we use to help with the intake. And for computer vision, yes, in autonomous, we do use computer vision. We use a limelight, and all we do is we just go up to the sub, scan for half a second, and then we'll turn, face the block, extend, and then drop down. We do a little bit of like wiggling, so the computer vision doesn't need to be too precise. For sensor-based transfer adjustments, I think I covered that.
Yeah, that sensing and automation is all really cool. And so you guys are also able to achieve some of the fastest teleop cycles in the world. And your driving style is definitely really aggressive. So what adjustments have you made to your intake and some of your teleop code to allow for this driving style? And how much practice do you do driving practice? And do you do anything special while doing drive practice?
Yeah, sure. So I guess like the main cycle speed just comes from like a lot of driver practice. So like I guess like pre-NorCal regionals, we did a ton of like driver practice without too many automations. So that definitely like helped with just with the extra automations being able to be like a lot faster. So there's also like a lot of software enhancements that help us have extremely fast cycles. So um I covered a little bit about this. Like we have the auto drive, the instant like override on the joystick, and then how the intake automatically unjams and will kind of act on its own without any need for driver input. So in terms of like the driving style being aggressive, it's mainly like possible just because the intake is so protected. Like if you notice at the front of our robot, we have a go tube, and that go tube is actually the pivot point for the intake, and the intake does not go further than that go tube. So like the intake is completely boxed up by our like very wide slide setup and that go tube. So we're basically able to like go into the sub, literally do whatever we want, and like if anybody tries to get in our way or if there's anybody like roughly near us, we'll try to give them like a little bump to kind of prevent them from intaking, because especially if they're using like a claw, it becomes very difficult for them to intake while we are kind of in the sub. If we just tap them a bit, it becomes like super hard to intake with the claw because you lose the alignment. And for us, like we can just be anywhere in intake. Like I can even intake like the wrong block and then it won't have any effect on us because we just shoot it out the back. So it's if I just want to like hit another robot or something along those lines, right? Like I want to mess up their intaking. All I do is like just deploy the intake and drive towards them, and the intake will filter out anything. It'll deal with any jams, and I'll probably get a block by the time they get tapped. Or if we just get a block early, then good for us. We have like a fast cycle, and then it'll automatically drive the other way. So, um, that's kind of how that driving style works.
That wraps up the presentation portion of our very first episode of Tesseract Talks. For anyone in the audience, if you still have lingering questions regarding anything about Turbo V8's intake, ask in the chat, and if time permits, they will be answered. The recording will be posted on our YouTube channel after the fact. We will be posting that later today. All right, well, I do have one question for you, Veer, and that's about how you iterated so rapidly. So you mentioned that having very small geometry changes of even a few millimeters really changed your intaking capabilities. So did you design your intake to allow these small features to be changed easily? For example, on some of our off-season robots, we included the Go Build a Pattern to allow us to mount parts without needing to do a full redesign. Do you do anything similar like that?
Yeah, sure. So our robot is actually like built on top of a strafer chassis. So in general, like we just have to go build a pattern everywhere. So um it's very, very easy to like iterate in that sense. In any custom parts where we know we might make any changes, we definitely like leave that pattern in multiple places. So I guess at least on our intake, like it's very, very modular. Like everything is held on by like um 3 or 5 screws or something like that. And it's just like you can access any part of it basically instantly. So like popping off like the top piece on the intake, it's like it's 3 screws per side and it just pops off and you can replace it. For the bottom piece, it's also probably like 8 screws and then you can just pop it off. For the actual like side plates, they're held on by 4 screws um after those I guess top and bottom pieces come off, but it is on a go tube, so we do have to kind of like take it off of the extension if we want to replace those main plates. So like those small like raising the intake more up, like those small like 1-2 millimeter changes, yeah, those are pretty tough to make once we have the intake finalized. There's no good way to like make those adjustable because we also want it to be rigid, so we can't add like any slots, and adding like a hole pattern, at least in that area, is impossible because just of the way the go tube is. But um for most of our parts, as much as we possibly can, we do leave as much adjustability as possible. And we have seen this be like very useful with the different parts of our robot, like our claw depositing system. We can like free build and kind of come up with a solution before we fully go with it. So yeah, that really does help with prototyping, leaving the whole pattern and using a strafer chassis.
Yeah, if there's no other questions in the chat, I have like one other question. So what kind of intakes and past teams did you take the most inspiration from when looking to design kind of a touch it, own it intake for this season?
Yeah, so I guess if I'm being honest, like I mainly looked at Skystone. So like the different people on our team looked at like different archetypes and whatnot, but there were a couple of like notable examples. So like one for that, at least that one with the lip, there was that intake with the lip, that intake horizontal. So not the same orientation as now, where we had that like arc lip with that thick base. We looked at like gluten free's Rover Ruckus intake. So that's where we kind of came up with the idea of trying to filter out the vertical blocks through that lip. But for Skystone, the side roller intakes, like the element looked pretty similar at the start, at least to like Skystone element. So like we were like, okay, we'll copy a Skystone intake, but um we were originally going to go with that, and it turned out to be like a pretty good solution, but it wasn't up to like standard after we found that that hot dog style intaking was much more effective. So um Skystone was like a really big season we looked at. Like again, like gluten free's intake was basically perfect that game. There were also teams like Technical Difficulties and Freight Frenzy that had a super effective intake, so that was also like some inspiration we took for our um kind of next intake. But honestly, like this year's element was so unique that like it was very hard to look at a previous year and figure out how to orient the block in intake, mainly because the grooves in the sample made it pretty hard to deal with. But um yeah, like there wasn't any specific previous season that gave us a ton of guidance, but just like general things like the counter roller, the top rollers being like effective, the hot dog style intaking, the other perpendicular style intaking, like all of those were just taken from different teams in previous seasons.
All right, yeah, that's really cool way to look at like different past seasons. So thank you all so much for attending today's episode of Tesseract Talks. We hope you all found this explanation of Turbo V8's blazingly fast intake really useful and gained some more insights for when you design your own subsystems. Huge shout out to Veer and Turbo V8 for their time, and we hope to see you all back for future episodes of Tesseract Talks.